Boom. Words, phrases, calculations, calculon. Calculon. Or whatever, something like that. Willkommen to another episode of Calc 2 Tuesdays. This time, we're going to do... Last week there was a little bit of theory going on. Not even really. It was really just a recap of why we care about taking integrals more than anything else. And so this week we'll review slightly some of those notions. And then we will also just start actually calculating some antiderivatives and probably even do some definite integrals as well. So let's just start by reminding ourselves of what the point of all of this is, right? So here, I'll make this little enlarge, enhance. Anyway, so an antiderivative, just by definition, right? It's just something that when you take the derivative, you get the opposite, or you get the original function back. Yeah. So this is pretty straightforward, right? Really, what the fundamental theorem of calculus tells us, which is pretty crucial as terms of theory goes. This is really why we care about all this, right? I talked about this last time. This is why we're doing all of this, is precisely for this reason. It's the fundamental theorem of calculus. It tells us that if we want to calculate a definite integral, like we see there, which again, remember, a definite integral is a limit of an infinite number of rectangles that have infinitely narrow width, right? That's one geometric way to think about it. But really what this tells us is that if we need to calculate definite integrals, the way to do it, assuming we have a continuous function, or at least piecewise continuous, we'll get more into that later, is to just find an antiderivative, right? And then we just have to evaluate. And that's what this business says, right? This says that if you want to find the area under this curve f of x between a and b, then you need to use the antiderivative, right? And any antiderivative will work. And we'll talk in a second here about how there's lots of different antiderivatives. So for example, before we start, let's talk about one other thing. Oh, I wonder why that didn't compile. Here, hold on just a second. Let's compile the homeboy. Let's compile the homeboy. Boom, boom, boom. So 1/2 of linearity just tells us that... Why didn't that... That's still not there, huh? Why? Why are you that way? Well, whatever. So the other half of... I'll just write it out. So linearity has two parts. The other part of linearity... I don't know why my LaTeX won't compile all of a sudden, but whatever. Silly old LaTeX. It's so techie. But anyway, so linearity says that... two things. So what I have on there is that if you take the antiderivative of a sum of two functions, you can just view it as the antiderivative, or the sum of the antiderivatives, right? Right? Instead of having to take the antiderivative of this big thing, I can just take the antiderivatives one piece at a time, a la Johnny Cash, right? Right? The other half of linearity says that if you take a constant, right? So C, let's just assume that's any constant, right? So if you take this and multiply it by a function, then it does exactly what you would like to do. You can pull the constant outside. Yeah. So this is super useful in point of fact. It's like one of the more, like without this, integrals would be brutally disastrous. Integration's already a pain in the ass. But if it wasn't for linearity, it would be just like damn near impossible. I mean, we'd essentially just have to do everything numerically. It wouldn't be worth it to try and calculate integrals analytically, like if, or not analytically, but symbolically, it would be pointless if we didn't have this. It would just be too much work to be worth it. Yeah, so let's use these properties. Let's just do let's build a table of integrals and then let's calculate some. So the thing to remember again, right, is that an antiderivative of some function f is a function such that you take the derivative of big F and you get the original little f back, right? So big F is an antiderivative of little f. Now here I'm saying on some interval, I mean, we can assume this is true. I mean, you can always break it down as long as it's piecewise continuous or whatever. But so suppose we have an antiderivative. Again, this definition is assuming this exists, and we'll see some examples later where antiderivatives don't always exist. But anyway, supposing we have one, it's an antiderivative if you take the derivative of big F and you get little f, right? I mean, it's the opposite of the derivative, right? And so that makes sense in terms of, for example, how we can start building up some knowledge about integrals. So for example, here's our first little integral table, right? Or antiderivative table, I guess I should probably have said. But typically when you look them up online, they all say table of integrals. Whatever. But anyway, so like we know, for example, that the derivative of x to the n is n times x to the n minus 1. It's like the first thing you learn in calculus, right? It's sort of like if you've ever worked at a grocery store as a cashier or in produce, like the first code you learn ever is for bananas 4011, and then you like never forget them. And if they're organic, they're 94011. Similarly, right, like if you are a new calculus student, like you'll never forget this derivative. There's also an important distinction here. We don't take this derivative when x equals minus 1. That's a special case, but it works for all the rest. And so what this means is the antiderivative has to do the exact opposite, right? And so instead of multiplying by the exponent and dropping it by 1, we divide by 1 plus the exponent and increase the exponent by 1. And then we'll talk about this little c here in a second. So let's just do a couple examples of those real quick, just to see it, just to get a feel for it, Just to see it, yeah. Gotta fix the lighting, yeah. It's all bad right now. Whatever, ooh. Wild West lighting. But anyway, so let's do an example. So for example, like since the derivative of x squared, right, is 2x, it stands to reason that the antiderivative of 2x, well, an antiderivative, right, of 2x would be x squared, right? But the problem here is that there's lots of antiderivatives like this, right? So, for example, certainly, this is a circle, right? I mean, we sort of go, and then this one just takes it right back, right? They're sort of opposites of each other. But this is not unique. Nope. So the thing to notice is that, right, derivatives don't care. So I know these look funky, but pretend this is like negative x squared plus 1, negative x squared plus 2, and negative x squared plus 3, yo. Plug and play. Yo. Anyway, so here's three functions, right? Negative x squared plus 1, negative x squared plus 2, negative x squared plus 3. Notice that at any point, right, like they're all going to have the same derivative. Right? I mean, the derivative of all these, negative x squared plus 3 is the same as the derivative of negative x squared plus 2, which is the same as negative x squared plus 1, and all of those are just equal to negative 2x, right? I realize I did positive there, but who cares, right? So what does this tell us? This tells us that the antiderivative is not unique. These are all antiderivatives. So the answer to this question is no. So there are infinitely many. Let's make a little note here. There are infinitely many antiderivatives. They're often referred to as a family of antiderivatives. The Adams family. Yeah. And so what we want to do is sort of classify all of them at once. And so the truth is that all the antiderivatives are just going to be the vertical transformations of this first one. So really what it is it's the antiderivative. You take a specific antiderivative, right here. This is a specific one. And then if we add any constant to it, we're going to get something that is also an antiderivative. And so that's what the plus c is for. So for example, continued. Yeah? So we know that let's say x squared and x squared plus 5 and x squared minus 25, x squared plus pi, x squared minus 2e, whatever, etc. These all have the same derivative. Namely, 2x, right? So then x squared plus any constant, right? So here, I mean, we're not going to do any like complex stuff. We're always going to assume everything is real valued. So c is any constant, right? So it doesn't matter, right? If I shift it up or down, that's not going to change the tangent lines, right? The slopes on the tangent lines are going to be the same, or the slopes of the tangent lines, I should say, will always be the same, right? It doesn't matter where I put them. Right? If I shift a horizontal line up or down, it's still a horizontal line. Yes, yes, yes. Boom, chicky, boom, boom. So that's why this plus c is there. And you'll notice it's there for all of them, because it doesn't matter. I mean, in that case, I did x squared or whatever. But it works for all of these in general. Yeah. Also, so another one, the next one, right? So we know the derivative of sine is cosine. And so just like before, right, because the derivative of sine is cosine, we know that the antiderivative of cosine is sine plus a constant, right? Strictly speaking, this is infinitely many antiderivatives right here, right? There's one for every single constant c in the real numbers, so not only are there infinitely many, there's uncountably infinitely many. So many, many, learning. By a similar, so the other ones are there too, right? So it's all the same idea. Right? The derivative of cosine is negative sine, so that means the antiderivative of sine is negative cosine. So on and so forth, like the derivative of tangent is secant squared, so the antiderivative of secant squared is tangent plus a constant. I know there's no c after the cosine, but this thing isn't compiling, and I'm not going to restart Vim. And then similarly for part e there, right? So here's a small table of integrals that we'll start to build. And so we can use these. And so let's use them. Let's do some problems. Oh, wait, here's two more. Sorry, they didn't all fit on the... Fix that formatting. Similar, like here's the easiest one in the world. So the derivative here, the derivative of e to the x is just e to the x. So that means the antiderivative is just e to the x plus a constant. So that's just like it was your favorite derivative back in Calc 1. it's rapidly going to become your favorite integral here in Calc 2. And then finally, we're going to talk more about this last one here in just a minute. So I say the derivative of the natural log of absolute value of x is 1 over x. That's probably something you know from calculus. We'll look at it in just a second. Verify that that derivative actually is true. But so then the antiderivative of 1 over x dx is the natural log of the absolute value of x. So let's talk about why is that absolute value there? Why? Pourquoi is it there? Calculus remix of me and Mrs. Jones. So suppose, let's try and figure out the derivative. This is important because we're going to have to talk more about the chain rule here in a second of the natural log of the absolute value of x. So if we're going to take this derivative, we have to remember the most important words ever uttered by Lindsey Buckingham. You must never break the chain. No matter what you do, you must never break the chain. Listen to the wind blow. Damn your love, damn your life. But don't break the chain. Whatever the hell else you do. So to take this derivative right, we got to do some chain rule. Well, we know this is going to be 1 over the absolute value of x, right? And then the chain rule tells us then we have to take the derivative of this inside function, which is the absolute value function of x, yeah? Well, fiddlesticks. I mean, what is this thing? Make my little shoulders shrug for shadows. Anyway, well, let's figure out what this is. So it might be useful to start with just, define the absolute value of x. It's typically done piecewise, yeah? There, put a little. There we go. Yeah, so there's nothing real surprising there, right? Like, that's just what absolute value does, right? If it's a positive number, nothing changes. If it's a negative number, you just flip the sign. So then it's from here, it's like really easy to see what the derivative is, right? What's the derivative of x? Oh man, that's such a hard derivative. Similarly, the derivative of negative x is just negative 1. Now here I got to make a little distinction though. So when you calculate absolute value just on its own, where you put the or equal to sign really doesn't matter because 0 is equal to negative 0, right? It doesn't make any difference. But over here it makes a difference. Tell me it made a difference, St. Bill. You gotta tell me it don't make no difference. But it does make a difference, right? Because what do we know about the absolute value function? If we were to draw said homeboy here, absolute, it's a Sith's favorite function, right? Only a Sith deals in absolutes, Anakin. Anyway, but notice here that at x equals 0, the derivative of absolute value of x doesn't exist, right? Because obviously the tangent line coming from this direction always has a slope of positive 1, and the one coming from this direction always has a slope of negative 1. And you're going to have a difficult time rectifying that limit. You're never going to get negative 1 arbitrarily close to positive 1, right? So that's why the absolute value, the derivative of absolute value loses the or equal to. Cool, so then we can, strictly speaking, we're going to have to look at the derivative of this thing maybe piecewise now. So if, x is greater than 0, right? Well, that means that 1 over x, 1 over the absolute value of x, times the derivative of absolute value of x, but since x is 0 or greater than 0, that's just 1, so that's just times 1. But also since x is greater than 0, absolute value of x is just x, so this is just 1 over x. Similarly, let's check the other side. If x is negative, well then the absolute value of 1 over x, well I'll write it out. Here again, in this case, right, where x is negative here, so the derivative is -1. But the absolute value of negative x is x, positive x, right? Because we take the negative of negative x, or whatever. So this will be 1 over negative x times -1, but that's just 1 over x. Sort of rambled a little bit there, but anyway, the point is, right, is that this actually is the derivative of natural log of absolute value of x. It's also useful in terms of thinking about the antiderivative, like natural log of x. You have to be careful because, right, remember, natural log is only defined on positive numbers. So that absolute value actually fills two roles. It makes the antiderivative more useful, right? Because 1 over x, you can take anything but 0. Got a stowaway. Mr. Insect wants to learn calculus. Welcome, Mr. Insect. But anyway, so that's the derivative, yeah? And similarly, for the exact same reason as everything else, that's exactly why the antiderivative of 1 over x is the natural log of absolute value of x plus c, yeah? So this is a super important integral. This thing comes up all the time. And it's at this point that I get to relay upon you, or relay to you, one of the greatest calculus jokes known to man. So here I'm going to post a little problem here in just a second. So let's suppose, let's make a variable. Maybe some of you already know where this is going. Suppose the variable, let's call the variable cabin is strictly greater than 0. So then, by our table of integrals, the antiderivative of 1 over cabin d cabin, well, what is that? So let's just go to our table real quick, right? We know that the antiderivative of 1 over x is the natural log of the absolute value of x. Now here our variable isn't x, it's cabin, but who cares, right? I mean, it's just the variable. So 1 over cabin d cabin, well, by our table there, we know that's going to be the natural log of the absolute value of cabin plus some constant c, right? But by assumption, cabin is greater than 0. So the absolute value of cabin just equals cabin. And so the antiderivative of 1 over cabin d cabin for all positive cabin is a natural log cabin by the c. Oh, Got to do all the Judge Smails laughs. The man's the menace. I sentenced boys younger to you to the electric chair. Didn't want to do it. Felt I owed it to them. Whatever. Okay, so let's do some antiderivative practice, eh? Let's just do problems for a while. So let's start with this first one. We're going to have to employ all sorts of tricks, and maybe you already know how to do this. Maybe this is like trivial for y'all. But maybe not. Who knows? Like maybe this is the first time you've seen it. So let's look at this first one. So let's find we're going to try and find the antiderivative of g of x dx. Now we're not going to worry about definite integrals yet. Like I'm not too worried about like trying to just evaluate functions. Like I feel like if you're listening to this particular recording, it seems likely that I'm trying to make the light better and I just make it worse. But whatever. So let's look at this crazy function g here. All right, here's g. It's this big long thing, right? But we also know that the integral is linear. And so what that means is that we can break this up into smaller, easier pieces. So let's just do that. Let's like walk through this thing, right? So this is going to be equal to the antiderivative of 4 times the sine of x plus 2 times x to the 5th minus the root of x all over x dx, yeah? It's not necessarily the greatest thing in the universe, but it's there. It's there, whether or not you want it. Okay, so, right. So let's use this linearity stuff and break this into simpler integrals. So the first thing I can do is break it into 2 pieces, right? Now I'm going to be a little bit more, with practice, you probably won't do quite this many steps, and some of you may be bored with me doing this many steps, but whatever. Get over it. Yeah? And now we can do the next step. We can use linearity again, and we can pull that 4 out just for funsies. Now we still got to deal with this one, and it's not clear maybe initially how to deal with this. Again, I'm being like, I would never write this many steps out in practice, but it's nice to see them all like being like sort of obscenely direct. So the key here to solving this awful thing is just to clean up the inside, and that's a key strategy. So let's make a note here, put a little dagger footnote down here. Cleaning up the integrand helps to integrate. Riemann integrals aren't good, they're integrate. Woohoo! All right. Anyway, so let's roll on. So yeah, the key here is just we got to just clean this inside up, right? So I got 2x to the 5th minus root x over x. Well, that's the same as 2x. I can't do it. I can't write all those steps out. I can't make myself do it. 2x to the 4th minus x to the minus 1/2. I just couldn't make myself do it. So why did this happen? Well, they're both divided by the singular x, right? So I can just divide both of these by x. So 2x to the 5th divided by x is just 2x to the 4th. The square root of x divided by x is x to the minus 1/2. Well, why is that? That's precisely because x to the 1/2, let's put over here on a note, right? The square root of x is the same as x to the 1/2. Yeah. Good. It's important to remember these exponential things. But now we can see, now this is cleaned up, it's just more of the same, right? And I realize we could have already just evaluated the sine antiderivative, but we'll get there. And then again, we can do this linearity business, right? And now we can tackle each one of these just in little, easy, simple pieces. Easy to manage, let's do it together. Anyway, so we know the antiderivative of sine is negative cosine, so this would be negative cosine of x. Here we're going to get 2 times the antiderivative of x to the 4th. So that's going to be 1 over 5 times x to the 5th. The great thing about taking integrals is it's super easy to check if you did them right. I can just take the derivative of this real quick and see if I get this again. What's the derivative of this? Well, the 5 comes down and cancels with the 1/5. And now this is x to the 4th. And the people rejoice. And then here we'll have what? Minus. So we have to do the same thing, right? So we have to add 1 to this. So this is going to be 1 over 1 plus 1/2. Or negative 1/2, excuse me, 1 plus negative 1/2. And then we'll have x to the 1 minus 1/2, yeah? And then we'll have a constant out there. Notice I only have one constant because if you have all three of these, it doesn't really matter because you can just add those three constants together and get this new one. So let's clean everything up just a little bit. So we'll have -4 cosine of x plus 2/5 x to the 5th. Now, this is a little tricky here. So this is going to be 1 over 1/2, right? So that's going to be minus a 2. And then this will be x to the 1/2 plus c. Bam, bada, bam, 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 bum, ba, bum, ba, bum, bam, ba, bam, beady, ba, 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 doop, doo, beady, ba, ba, da, ba, doop, doo, zippity, bobbity, boobity, bobbity, boobity, bobbity, boobity, doo. Yeah. Okay, that was pretty easy. Let's do another. Come on, how about another? Let's do something that really cooks. Let's skip these next two. Those are pretty much just the same. Actually, no, let's do B real quick. So let's do B. To do B or not to do B. I always do B. Oh. Hamlet was dumbass. Just kidding. So here's our function. We want to find the antiderivative of this guy. The easiest thing to do here, right, is just convert this to exponential notation. This is x to the 3/2, right? Because this is x to the 2/2, and this is x to the 1/2. So you get x to the 3/2 total. So then the antiderivative of x to the 3/2 is, this is not too bad, right? It's 1 over 1 plus 3 over 2. Times x to the 1 plus 3 over 2 dx. And yeah, so that's no big deal. I mean, we just got to add these up. So this is what? 2/2 plus 3/2 is 5/2. So that's 1 over 5 over 2. X, so it's going to be the same up there. 5 over 2. Plus constant. And then this is going to flip, so this will be 2/5 x to the 5/2 plus c. So this right here, this is an infinite collection of antiderivatives. But if we notice, sure, I'll put the big capital notation there. What this is saying is that, right, we want to find the specific, right? For every real number c, there is a unique antiderivative, this guy. But for this case, we want the very specific antiderivative. Oh, you probably can't see it. Here, let me hide that problem back on the screen. Oh, you can see it. Perfect. Yeah. So yeah, right there. We want to find this. Yeah. So we need to have this function, right? There's infinitely many of these f of x's, but there's only one that goes through the point 1, 2. So how do we do that? So we know that f of 1 equals 2, but that also equals 2 over 5 times 1 to the 5/2 plus c. So 2 equals 2/5 plus a constant. So 2 is what? 10/5 minus 2/5, so 8/5. That sound right? Looks that way to me. So this specific antiderivative is 2/5 x to the 5/2 plus 8/5. Yeah. Yeah. Let's do the next one, yo. So, up next we have... actually, no, I'm not going to do that one. That's an exercise. Let's go to part D. So, for D, let's use a blue pen. Seem to have more contrast. So here, so a of x is 2x times e to the x squared. We want to find the antiderivative of this thing. So this is a little tricky, right? Because there's, like, first of all, this has not appeared in the table. I mean, x is in the table, and e to the x squared is in the table. But 2x e to the x squared is not in the table. So this again should remind you of Fleetwood Mac, right? Watch the sunrise, bing, 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 down, 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 down. And if you don't love me now, this should make you remember the chain rule. This looks like something was chain ruled. Let's take a look at it. Or whatever. So if we think about this function, there's sort of two parts, right? So if I look at this little piece right here, and this little piece right here. So let's suppose I called this little piece u. In particular, I'm gonna just say, I'm gonna substitute u equals x squared. Well, notice something then. It's pretty obvious that du then is 2x, yeah? I mean, that's just the derivative, right? If I take the derivative of both sides of this function, I guess I'm being sort of fast and careless here. But essentially, I can do this, right? This isn't too crazy. But the thing to notice here is that this is the derivative of this thing, right? May call it d dx, yeah. So in a situation like this reminds us of the chain rule. So let's recall how the chain rule works. The chain rule says if you take the derivative of a composition, yeah, right? So if we take the derivative of a composition, this is the derivative of the outside function evaluated at the inside function times the derivative of the inside function. So notice here our outside function is e to the x, yeah? And our inside function is x squared. Notice that we get the derivative of the outside function, e to the x, which is just its own derivative, evaluated at the inside function, which is our x squared, times the derivative of the said inside function, which is the 2x. So let's substitute. So let's take a look at this integral. So we have the integral of, or the antiderivative, I should say, of 2x e to the x squared dx. So I'm going to use this substitution. I'm going to replace 2x dx. This is du. And this right here is e to the u. Yes, yes? So then this antiderivative becomes the antiderivative of e to the u du, which is, I mean, that's about as easy an antiderivative as there is, yeah? I mean, e to the x is everyone's favorite antiderivative. It should be. If it's not, it will be soon. So that's just e to the u plus c, and now we just substitute back. Oh, and this is how we substitute. I mean, if you really hated yourself, you could also do this with integration by parts, but we'll get to that later. Pretty much any integral you could do any other way, you can probably do with integration by parts somehow or other. We'll probably spend a lot of time on integration by parts. It's like the most important thing in the universe. There is nothing greater. You must go forth, my child. Okay, cool. So let's look at another. How about another? Man, that Marvin Berry concert, man, when I was a kid, that was something else. Okay, so let's do b of x, eh? B of x is 3x squared, x cubed minus 43. So again, we want to look for a piece of x, or a piece of b of x, I should say, that is the derivative of some other piece of b of x. That's the goal. Well, I mean, there's a couple choices, right? I mean, obviously, there's something with the x cubed and the 3x squared, right? But what? What is it exactly? Well, so let's do some scratch work over here. We'll switch to purple for scratch work. Because there's two choices. We can either choose, I mean, maybe it's obvious this one to choose. We could either let u equal x cubed, or we could let u equal x cubed minus 43. Right, because in either case, du is going to be 3x squared either way. But one of these is way better than the other. You should choose one and not the other, because if you choose the other, that would be bad. But anyway, so choose the other one. Like, which one should we choose? Well, I mean, let's just try. So if we take the first one, like, suppose we just do x3, well then then we'd have what? B of u, right, equals du over u minus 43. So if it's just du over u, that's great, right? But this du over u minus 43, nope. So we don't want to use this one. We want to use this one. So so now we can just do our substitution, right? This is the substitution we're going to do. So the antiderivative of b of x dx, right? Well, that's the same as the antiderivative of 3x squared over x cubed minus 43. And then we do our little substitute. So the top is going to be du dx. Whoops. And the bottom is just going to be u. So we'll get du over u. But this is just a fancy way of saying 1 over u times du, right? Which we know to be the natural log of u, the absolute value of u, plus a constant. And then we just substitute back, so it's the absolute value of the natural log of x cubed minus 43 plus c. Yeah. Whatever. All right, let's do part F, Mr. F, and then maybe we'll do like an actual integral instead of just these antiderivatives. So c of x is negative 4x e to the x squared. Well, so obviously, right, I mean, this is the obvious candidate for u. It's also the correct candidate for u. So if u equals x squared, then du equals 2x dx. The problem, though, is that we don't have negative 4x here. right? Actually, the problem is we have negative 4x here. So what can we do? We can just, we'll just be a little slick with our writing here. So that the antiderivative c of x dx. Well, there's different ways to think about this. I mean, you could just divide by 2, basically, but whatever. But in this particular case, actually, let's just do that. So another way to think about this is that 1/2 times du equals x times dx, right? So here we're going to use all sorts of tools. We'll use linearity. We'll pull linearity out. We'll pull everything out of the box. So this is the antiderivative of negative 4x e to the x squared. And so let's do our substitution. Well, actually, before I do, let's use linearity real quick. This is the same as negative 4 times the antiderivative of x. E to the x squared, yeah? And then let's just go ahead and substitute. The nice thing is, since this negative 4 is outside, I don't have to worry about it anymore. So x dx is the same as 1/2 times du, and then x squared just becomes u. So this is just negative 2 e to the u plus a constant, yeah? Don't you just love taking integrals of e? It's the best, yo. But again, we back substitute. Yeah. And that's it. In the words of the great Montel Jordan, this is how we do it. It's Tuesday night. I feel alright. The party's here on the whatever side. Yeah. Anyway, so there's that one. Let's actually do let's use that same sort of nonsense and let's actually calculate a definite integral. So let's go from, say, the natural log of 4 to the natural log of 10 of, let's say, 2 times e to the x dx. So we want to try and calculate this thing, right? But before we do that, let's just remind ourselves how we do that. Well, what do? If we want to find the definite integral, we use this business right here. It's the fundamental theorem of calculus. It puts the fun in fundamental. It's the fundamental theorem of calculus. And if you don't appreciate it, it will come for you. Not really. You'll just do bad on exams. Whatever. Okay, cool. So, yeah, forget this one. Let's just do a couple problems and then call it a day here. So let's make this a little. That's fine. Okay. So the first thing, let's think about what this means geometrically. So 2 times e to the x, right? It looks like, right? This is what the point 0, 2. Here's the point 1, 2e. Etc. And then somewhere over here, we'll just say, I don't know, it's probably right around here. We'll say this is the natural log of 4, and then over here somewhere, I don't know if this is probably not correct, but whatever. No, the natural log of 10's got to be more than 1. We're good. Cool. So what is this? This integral, remember, is this area. The area is equal to this integral. Which is what we're finding, right? I mean, geometrically, that's what we're after. That's the point, yeah? So let's do it. Well, this is the easiest antiderivative in the world to take. So first we have to find, let's find a antiderivative. for 2e to the x, which is 2e to the x. Strictly speaking, it's plus c, right? But the fundamental theorem of calculus says I can do it for any c, so who cares? I'll just choose c to be 0. It actually doesn't even matter what c you choose, as we'll see in just the calculation here in a minute. Forget the c. We don't need it. Anytime you're calculating a definite integral like this, you don't ever have to worry about the constant. Who cares about the constant? Shouldn't care of the constant. The constant. The constant. The constant. Whatever. So, okay. Let's see. Come on, brain. Too many things going on at once. Oh, yeah, so that's easy peasy, right? So then this is just going to be... so 2e to the x dx. Sorry, I spaced out there for a second. Right, well, this is just going to be 2e to the x. Now, this notation here is just saying where I'm going to evaluate it. It says this notation means exactly what I'm going to write down. It means I take 2 times e to the natural log of 10 minus 2 times e to the natural log of 4. And now you will see why I chose points inside the natural log. Because e and natural log are inverses of one another. Oh yeah, oh yeah. 12 is the answer, baby. 12 is the answer, 12 is the answer, 12 is the solution. Isn't that great? It's probably not that great. But anyway, so yeah, there's a definite integral, and that's the whole point of, putting up these horrible intervals, or integrals, yeah. The nice thing is we can just keep doing it, right? Like we can take... So let's make a little note here. This is what we'll finish on. We know from differential calculus that in certain cases we can take many derivatives of a function. So why not many antiderivatives? Pourquoi pas? And the reason, the answer is there's no reason why not to, especially once you get into like vector calculus, man. You're taking multiple integrals all the time. But let's solve this is the final example for this evening. Let's solve how to write the word solve. There you go. Let's make it sound really cool. Let's solve a differential equation. Let's say f. Oh God, what have I done? Okay, no, I think we can do this. I just got to do trig in my head. I'm like, well, I'll just make up problems. Like, so let's suppose the second derivative of x, let's just make it easy, equals, how about 2 sine of x plus 3 cosine of x. So what does this want us to do? This wants us to find, in particular, we need to find a function f of x such that this is its second derivative. It should be okay. Well, whatever. So let's think about it. So this is a little more interesting, right? We got to be a little careful here. So let's just take one antiderivative. Let's just see what happens. So let's try to find. So f prime is an antiderivative of f prime prime. Yeah? So the first step should be to find f prime. Said another way, right? F prime was the antiderivative of f prime prime. Yeah? Which makes sense, right? Because if you take the derivative of f, you get the second derivative, right? And if you undo the second derivative, that takes you back to the first derivative, yeah? Bam, 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 bam. Pew, 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 pew. So we'll play it a little fast and loose here. So let's just start with a very simple. So we've got what? 2 sine x plus 3 cosine of x. Yeah? So let's just take a couple of antiderivatives. We'll worry about constants next time. Okay, so we can break it up into pieces, right? This is the same as 2 times the antiderivative of sine of x dx plus 3 times the antiderivative of cosine of x dx, yeah? So this is going to be negative 2 cosine of x dx plus 3 times sine of x plus, let's call it constant 1. Right? So we're halfway there. And if you're looking at this thing, you should already be able to see what the answer is. I had a professor in undergrad told me once, it was like, he actually said it's this whole, I was taking like, I think it was like a advanced calculus class kind of thing, like a bridge into real analysis or whatever course. And like, he was like, it's like stuck with me forever. It's like the easiest differential equation is the one you already know how to solve. And that's the case of these. Anytime, you'll, after a while, just be like, wait, the second derivative is the same. But anyway, we're halfway done, right? We need to find f, and we've gone from f prime prime to f prime. So let's just go one more step. So this is the exact same notion. So f is just the antiderivative of f prime, which, as we just found out, is the antiderivative of negative 2 cosine of x plus 3 sine of x plus, okay, now we got to be careful here. We have a constant. What is the antiderivative of a constant? Well, a constant, strictly speaking, is just x to the 0, so this becomes c1x plus our second constant. Shoot, that was too early. Yeah, what am I doing, dude? I'm getting way ahead of myself. Sorry. Dummy. I like started taking the integral halfway through. But anyway, so let's just do it again. So this will be what? So we know that negative 2 can come out. Plus 3 sine, the 3 comes out. Yeah? So we know that the antiderivative of cosine is negative sine, so we'll get the negatives cancel and we'll get a positive 2 sine of x. Here the antiderivative of... No, that's still negative, silly. Yeah. And then this becomes negative, yeah. It's a good thing I'm almost done for the day, because I'm just writing complete gibberish now. Goodness gracious. It's really hard for me to just do the not do them. And that's actually our answer. I'll write it nice and clean. Yeah. Words and phrases are coming today. Yeah. So yeah, that's the ticket. Now we could put numbers in there or whatever. But what's interesting to know here is we actually found a whole class of generally speaking, if you have the if f equals negative f prime prime, which is what happened here, right? Our second derivative was essentially the negative, and we could make these 0 if we had to. The second derivative is the same as the first one, essentially, right? And so this implies that it's trig functions that have this. In particular, sines and cosines have this nice property where if you take the second derivative, you get the original function back, but negatived, which really means that if you take the fourth derivative, you get back to where you started from, right? So in a certain sense, and it should come as very little surprise to anyone who's seen any complex analysis or ever seen Euler's formula, that when it comes to derivatives and integrals and just life in general, that e to the x and sine of x and cosine of x, and then consequently all trigonometric functions have a very deep intertwined relationship, right? E to the x and sine of x, and especially once you allow I to start running around, magic can happen. It's palindrome time if you're using military time, which means it's time for me to call it a night. See you tomorrow or next week, you feel right. I am done. Oh, wow, wow. See you next time.